Photography, the art of capturing a moment and keeping it that way forever. Behind every art, however, is a science, and in particular, chemistry. I am Dr. Patrick Westervelt, and today we will be taking that art, that science, that beauty, and explaining it to you. Welcome, viewers, to the most amazing photography-related project on this side of town, the Gibbs side. In this project, we will investigate each aspect of the art known as photography. The history of photography will be explained, and it will lead way to the way that the camera works. The steps of developing pictures will follow, and a report of the lab used to develop my actual pictures and the film development. The science behind photography will, in these, be accentuated through the whole project. The project will conclude with my finished pictures, a formal conclusion, a glossary, and list of references. Beginning with the history of photography, the project formally begins now. Alhazen, pardon the pronunciation, invented what is considered the first camera around the year 1000 AD. At this point in time, however, the camera was only used for things such as drawing and observing. In 1827, Joseph Niesmore Niepce took what is considered the first photograph, but his photos were very different. They required hours of exposure to sunlight, and after revealing their picture, it would fade over time. Louis Daguerre was experimenting at a similar time, and eventually developed a way to make photographs that did not fade over time and had a relatively low exposure period. Daguerre and Niepce eventually collaborated, and even though it was only finalized after Niepce's death, the daguerreotype was eventually created, which is the template for all forms of photography. The daguerreotype allowed images to stay on the film by having them washed in silver chloride. Daguerre and Niepce's son sold the rights to the daguerreotype to the government, and within years the process became extremely well known. In the years that followed, several innovations were made. In 1841, Henry Fox Talbot developed the first negatives. In 1851, Frederick Scoff Archer invented the wet plate negative. In 1889, George Eastman invented the flexible film roll. Color photographs, Kodachrome, were invented around the 1930s and became widely available and used in the 1940s. In 1963, Polaroid film was developed, allowing pictures to be taken instantaneously. 1984, move over George Orwell, birthed the first digital camera and developed by Canon. Today, further developments are being made in all types of cameras and will continue into the future.
Also worth noting is Johann Heinrich Schultz. Schultz discovered silver nitrate in the 1700s, an obviously important part of making cameras retain their images.
Now, most cameras are made of very similar parts. Cameras have three primary parts: the lens, the film, and the mechanical part of the camera itself. These three parts equate to the viewing portion, the chemical recording portion, and the, mechanical portion. The lens of a camera is a piece of glass that detects light. The light from other objects bounces off of them into the lens, where it is temporarily stored. It is able to do this because the light moves from the air into the glass, where it travels more slowly. The light is redirected and pointed at the same place, where the image begins to take form. After the image is recorded in light, it's time to make a chemical recording of this picture, otherwise known as the film. The film is mostly made of gelatin and plastic. Films have many light-sensitive grains on them that begin undergoing chemical reactions upon their exposure to light. In development, the grains are exposed to other chemicals, which begin causing a new reaction to take place, causing the picture to develop. This development forms a negative, where darker areas are lighter and lighter areas are darker. When the pictures are finalized, it is converted into a positive, which is just an average picture. Light areas are light, and dark areas are dark. We will get to this process shortly. The camera, obviously, only handles part of the process of pictures. The other obvious factor in the development of pictures is the, development.
I am now going to go over the various parts in the process of developing the picture and explain why each are important. For the exact chemistry of each of them, you will have to see a later part in this series. Exposure. The light-sensitive grains on the film are exposed to a light reflected through the camera's lens. The grains undergo a chemical reaction. Development. The film is placed in a developing agent. The grains exposed to light are converted into metal. The grains that were exposed to light will be dark, while the grains that weren't won't change or won't be seen. Stop bath. To end the development of the film, it must be washed in a stop bath to stop the grains from reacting. Fixation. To clean the film, it must be placed in a fixing bath. The bath removes the grains that weren't exposed to light. Washing process. The leftover chemicals are washed off of the film with water. I will now be answering some very specific questions about the development of film. Film is made from emulsion, light-sensitive grains. The emulsion helps the negatives develop, producing the picture on the film. Agitating a developing tank is crucial to how the picture will turn out. If not agitated, chemicals in the bin will reach its limit and not do the job. If you agitate it too much, streaks will appear. Temperature plays a vital role in developing film. Adding heat to any of the chemical processes will speed up the process. If the temperature is too high, the emulsion of the film may melt. If it is too low, there's a strong chance that the chemical process won't happen at all. The washing process is also very important. It prevents chemical contamination and keeps the film from being damaged. If the fixing bath is not washed off the film, it will later deteriorate the film itself.
Important terms and variables in this process include the following: agitation, which is when the dish/tray is rocked, and when done incorrectly, the picture will develop incorrectly, with streaking or straining. The temperature is also very important, as heat can cause parts of the film to melt and reactions to happen too quickly. Likewise, environments too cold will likely lead to chemical reactions being slowed, or not happening at all. The focus of this project is on chemistry, so obviously photography has quite a bit of that going on in it. The various parts of film go through a whole bunch of chemical reactions during the process of development, which has already been described here. Here, we get to see the nitty-gritty of each of these steps, and how things change. For example, when silver bromide gets activated with light, it turns from an ion to a metal, which is what helps create the image. The chemical equation is just from ion to metal, AgBr to AgBr. The stop bath solution is the next thing to be added. The chemical equation is 2AgBr to 2Ag plus Br2. After this, the mixture is watched, so that part of it returns to how it once was. Water is obviously added, which causes the following reaction to take place: H2C2H3O2 to C2H3O plus H2O. After this, the fixer solution is put in, causing the final reaction to take place: 2AgBr NH4 to S2O3 to NH4Br plus Ag2S2O3. The film is finally washed to get rid of any miscellaneous chemicals, ridding it of any compounds besides the final one. Welcome to part 6 of this video. In this part, we are going to go over the procedure as you would in a lab notebook, beginning with the objective. How are photographs developed? Now the procedure. Put on safety glasses. 4 beakers must be obtained. The canister must subsequently be gotten, a double canister if you have 2 films, or a single if you have 1. Once the film is sealed, the canister, the film cannot be opened. Only the red cap can be to fill it with liquid. A 400 milliliter beaker must be filled roughly full before being poured into it. Label the beakers as the following in order of use: water in beaker 1, developer in beaker 2, stop bath in beaker 3, and fixer in beaker 4. These first 4 solutions must be gotten before the start of the experiment and made 20 degrees Celsius. Each group must obtain 2 aluminum pans, one on a hot plate with water, the other on the bench with water and ice. Everyone gets a thermometer and monitors the temperature of all 4 beakers. Once all 4 solutions are obtained, one person begins doing the 4 solutions. The timekeeper, next to them, makes sure all is on target. Agitator pours the first solution in the water. Pour in, see when it reaches the top, and close it. Water must be in for 1 minute to pre-soak. This loosens the emulsion. It agitates. This is done over the sink since it can leak on occasion. The main way to agitate is to flip it upside down, moving it side to side, or spin it in a circle. Agitation means rotate between the 2 methods. Watch consistency. If it goes too fast, the reaction goes too fast. Overdevelopment occurs, and if it is too slow, underdevelopment. The water must be agitated for 30 seconds and rest for 5 seconds. When it's time to empty, say time. Shake to make sure all the water is out and fill it with developer. The developer must be in the canister for 9.5 minutes. Agitate for 30 seconds. Agitate until the timekeeper says to stop. rest for 60, agitate for 5 seconds, rest for 30 seconds, and keep going. Developer is the most important step. Once the developer is empty it out in the sink, then immediately put the stop bath in. This is to stop the reaction. If you hesitate, overdevelopment may happen. All members in the group must have perfect timing. Close it up. Stop bath is in for 2 minutes. When done, empty it out. Before the fixer goes in, it calls for 2 wash and dumps. Fill it up with water, close it, and shake it 15 times. 2 counts of 15. Once done, the fixer goes in. Time to set up on the back of the timesheet. It stays in for 7 minutes. Fixer, once done, does not get poured down the sink. Pour it back into the beaker, put it back inside where the fixer is, or there could be serious damage. After the fixer, wash 10 times with water. 10 times 15 is 150. Then the agitator has been doing it for a long time. After second of 10th wash, someone takes over since the person may be tired. In the meantime, the rest of the group should be cleaning out beakers and getting permawash and photo flow. These have no temperature they must be at. As soon as someone has taken over the wash and dumps are done, the permawash goes in and stays in for 1 minute. Once dumped, the permawash is a soap, which means wash and dump 30 times. Whatever is trying to be removed must be washed out properly. Add the photo flow and shake it. Contact your advisor to make sure it is done, clean it, and see how the pictures look. That is it. In terms of observations, I was not present on the day of the procedure, so my observations are somewhat limited. One thing I certainly was able to observe was the fact that one of the photographs came out overdeveloped. This is likely because one step in the process we did something slightly off, such as having the developer in too long, or letting one of the other chemicals sit, or improper cleaning methods. However, since it was only one photo, it's very likely that this was merely a fluke. As they say, practice makes perfect, though. For other observations, even though I wasn't there, I've secured video footage of the procedure happening, so I'm going to play, after I'm done with this section, a short montage of various parts of the sequence. Using the process we learned, we were able to develop pictures. One of our pictures ended up coming out overdeveloped, which means in one of the steps, we may have made an error. On a whole, though, we accomplished our goal of developing the pictures. The lab used skills we had been learning about all year, and we'd been using in other labs. In addition, it tied in quite well to the chemical reactions chapter, although a more definite conclusion is approaching that will show how it ties into everything.
For the coolant. We do.
This scent is like
Over here in the sink, everything is always over the sink, so the solution should be here.
Stop it. 8, 7, 6.
Sherry, next time make sure that solution is right there.
3, 2, 1. Stop. Wait, it was right there when he Oh well. Let me know when the lid's on, okay? Okay, immediately put that in. Okay, and stop. 30 seconds.
Okay, 1, 2, 3, 4, 5, 6, 7, 8.
After you do the stop bath, you have to wash it with water.
More because you're the last group.
Empty.
Instead
Well, there's
of
20
400
second rest, so
milliliter, if you're
I don't know.
single, get 375.
Yeah,
And
4,
those of you with
3,
600 get
2,
575.
1,
Make
empty.
it so that everyone has it.
Now what do we wash it with? What? Yeah.
Take the holes.
50. Okay. Ready for
Who's
the next
ahead?
solution?
You're ahead.
This is fixer, right? Okay, it's only 7
Be
minutes.
careful with the fixer. Make sure the fixer goes back once you dump it in an original beaker. That's the perma wash. So that'll put it
Ready? And go.
It doesn't have to be.
Okay. 5 seconds before you agitate. Go. Stop.
Is that the answer fixer? When you're done with the fixer, all fixer get poured into this bottle here.
two.
If you're on
The perma wash. Ooh, at least we don't have to do. Should I clean this stuff up? We'll clean it after. Okay. That's what, 9? I thought perma wash should be on the wall. That's perfect. Yeah, I know. Water's so cold. 1, 2, 13, 14, 15. 23. Yeah, sorry. 1, 2, 3, 4, 5, 6,
the moment that goes in the back, not in the front tray.
11, 12, 13, 14, 15. Done.
You want to make sure you wipe the floors.
Yeah.
Yes, and just wait for me.
So the film can be exposed to light now?
After the picture. You got some uneven development.
Looks cool. It does.
You lost quite a few of them. We'll discuss that later. Where's your label?
Right here.
Put it on the top of this. Yeah, do it around. No. Push it through. Like this.
Oh,
And then wrap it around. More, because you're the last group.
empty.
Instead
Well,
of
there's 20 seconds
400
rest, so
milliliter, if you're
I don't know.
single, get 375.
Yeah,
And
4,
those of you who are
3,
600, get
2,
575.
1,
Make
empty.
it so that everyone has it.
Now what do we wash it with? What? Yeah.
Take the holes.
She's hanging it like. I think so. Are all theirs colored? No, they got like 3/4. All that I have. Yes. And then we have to clean the floor. Yeah. We have. So we have 12 at 1. 5? Like we definitely could have, especially what? We definitely could have beat it.
Many chemicals were used in the process of developing the pictures, and they were mentioned what they did, but what was not mentioned was what they were made of, which I will now go over. The developer, a Kodak professional, was made of metal 2 C7H9NO and HSO4, which is bisulfate. Next is the hydroquinone, which was C6H6O2, sodium carbonate, which is Na2CO3, and sodium sulfite, which is Na2SO3. Next we have the vinegar, which is just acetic acid, which is C2H4O2. Next we have the fixer, which is made from 2 solutions. Solution A is made from H3N1 and 2H2O3S, ammonium sulfite. Next is sodium bisulfite, HNaO3S. Then is ammonium thiosulfite, N2H8S2O3. Next is sodium acetate, C2H3NaO2, and H2O, water. Solution B was made of sulfuric acid, H2O4S, aluminum sulfate, Al2SO43, and H2O, water. Next is permawash, which is made of H3N1, 2H2O3S, ammonium sulfite, and sodium sulfite, Na2SO3. Last is the photoflow, which is made of p-cetera-oxyphenyl polyethylenoxyl alcohol, C21H42O3, which is propylene glycol, and water, H2O. Alright, now I'm going to cover the part where I discuss my pictures, what is in all of them, and what chemicals make up all those things. One thing of note is that dealing with humans, and also dogs in the case of one of my pictures, I will not be discussing what makes them up until the end, because I'm doing that separately since it is a very complicated thing. So, let's begin. Picture 1 has a dog, a garage, a basketball hoop, snow, pavement, and trees. The dog will be covered later. The garage is made of paint, which is made of CH2CHCOOH, and wood, which is made of cellulose, C6H10O5, and lignin, roughly C31H34O11. Next we have the basketball hoop made of steel, Fe3C, and string made of cellulose, C6H10O5, and water, H2O. Next we have glass, which is made of SiO4. Next up is snow, which is made of H2O. The pavement is made of cement, which is made of calcium oxide, CaO, silicon dioxide, SiO2, aluminum oxide, Al2O3, and iron oxide, Fe2O3. Lastly are the trees, which are made of bark, cellulose, C6H10O5, and lignin, roughly C31H34O11, and the wood, which is made of very similar material. In picture 2, we have the school, which is made of bricks, silica, SiO2, alumina, Al2O3, and limestone, CaCO3, as well as cement, which was covered, and paint, which has been covered. The tower is made of steel, which has been covered, and circuits, made of CH2CHCl. Next is snow, H2O, the gate, which is made of likely steel, iron, Fe2, playground, which is made of plastic, CH2CHCl, and paint, which has been covered. Next we have the trailer, which is similarly made of steel, Fe2, and paint, and sidewalk, which is made of cement. Trees have also been covered, and we have power lines, which are made of wood, which has been covered, and aluminum, Al, as well as steel, Fe3C. Next we have picture 3. In this there is a chair, which is made of iron, as well as cushion, presumably wool, which is an organic material and likely made of carbon, nitrogen, and oxygen in this case. Also in there is snow, H2O, a gate made of steel, covered, a fence made of wood, covered, and a bush, which is similar to a tree, which has been covered. In picture 4, we have a gate made of steel, which is covered, snow made of H2O, which is covered, a tree, which has already been covered, a house made of paint, which has been covered, wood, which has been covered, glass, SiO4, and cement, which has been covered, a playground made of plastic and paint, both of which have been covered. Next is picture 5, which has a phone tower, which has steel, which has been covered, and wires, most likely made of Fe2. Snow, H2O, dirt, made of stones, which is made of many different elements, but primarily SiO2 and CaCO3. Sand, which is also made of many different materials, but likely many of the same ones as stones. Clay, also made of many things. Trees, which have been covered, and clouds, which are made of water, H2O. In picture 6, again, there is a stone, which is made of many things, including SiO2 and CaCO3, a chess set made of plastic, made of CH2CHCl. Trees, which have been covered, snow, water, H2O, a person, which will also be covered later on, a playground made of plastic and paint, covered, clouds made of H2O, houses, which have already been covered, and a bench made of wood and steel, which have been covered. In picture 7, there is a couch, which is made of wood and cushion, which have both been covered, although the cushion I also included that it may be made of feathers, although those are made of largely the same material as wool since they're both organic materials, carbon, nitrogen, and oxygen. Table, which is made of wood, which has been covered, glass, which has been covered, and copper, which is Cu. Next we have the binder, which is made of paper, C6H10O5, cloth, C6H4COOH2, as well as carbon, nitrogen, and oxygen, and metal, Fe2. Next we have leather case, leather which is made of C2H3Cl if it is made inorganically, and if it is organic, it is made of largely the same materials that have been listed for organic materials, such as carbon, nitrogen, and oxygen. Cardboard, which is made of cellulose, CHOH, and paint, which has been covered. Plastic has been covered, which makes up the plastic. Paper has been mentioned. The styrofoam is made of polystyrene, which is made of C8H8. Books are made of paper, which has been covered. Ink, which is made of CuNH4 2SO42. C6N6FeK3. C6N6FeK4. And NH4 2FeSO42. And leather, which has been mentioned. The floor, which is made presumably of cotton, which has been covered, and nylon, which is made of carbon, hydrogen, nitrogen, and oxygen. Lastly, we have picture 8, which includes the television, made of CH2CHCl, making up the plastic and circuit board. Trophies made of plastic and paint, which have been covered. Cardboard, which has been covered. Paint, which has been covered. The shelf is made of wood, which has been covered. And nails, which are likely just generic steel, such as Fe2. The Legos are made of plastic and paint, which have been covered. Clay is made of synthetic plastic, which is CH2CHCl, as well as polymers, CH2CH2. Paper, made of, covered, sorry. Paper makes up cards, paper, and ink make up the books, and that is all of my pictures. Now I'm going to cover what humans and dogs are made of, since it's mostly the same stuff, since they're both living beings. The proportions for this part are not going to be exact, because they vary with each living being. I will just give what it is made of in terms of which element, not quantity. It is made of H, O, N, C, A, P, S, N, A, K, C, M, G, S, I, F, E, Z, N, C, U, M, N, C, R, S, E, M, O, and C, O in conjunction to varying degrees. And then other stuff humans are made of are just stuff like Na, sodium, O, oxygen, C, carbon, H, hydrogen, and then hemoglobin, which is made of stuff like CHO, Fe, N, and S. And so ends this exciting project. Now for reference, I'm going to show the negative versions of the film, the ones that I have. It will be slightly hard to see them. Yes. Even though I did my best to explain most of the terms used in this video, I'm now going to go over some important ones to review. Emulsion. Layer on top of the film holding silver bromide. Canister. It holds the film reel. It is used to safely mix the film with any chemicals it needs to be in the absence of a red room. Fixer. The fixer is a chemical in the film developing process, added after the stop bath. It removes any of the silver bromide that wasn't exposed to light so it may not be converted so that they are visible. The reel holds the film in its container. It makes certain the film has enough space between itself to have chemicals come across all of it. Photographic paper. Film. Stop bath, added right after the developer. It makes it so that silver bromide on the film will stop converting. This is a collection of every work that I have cited in this video.